So when we're dealing with beam analysis, there are three things we have to check. One is bending stress. That is the FB. Remember, this is where you take the bending moment off of the moment diagram and you plug it into your formula. Second thing we have to check is shear. And this is both longitudinal and transverse. And fortunately, when you find them, the longitudinal shear and the transverse shear are equal to each other in a beam. And there's where you use the shear diagram to get the value of the shear at that point. And normally what we just do is we take the largest value of shear and we analyze the beam off of that. And then the final thing we started to discuss at least on Tuesday, is deflection. How much can that beam be displaced vertically from its original position before it causes problems? And remember, we discussed that most of the time limits on deflection are not necessarily structural. A beam can usually bend or sag a considerable amount before it really compromises its structural stability. It's other factors like plaster and sheetrock ceilings and stuff like that that limit the deflection. One possibility, especially if you're dealing with like a flat roof, you don't want it to sag too much because you're going to get water ponding in the middle of the roof. Of course, then the water ponds, it deflects more, then more water ponds, and it can be a bad cycle. So let's take a look at a beam. This beam is going to be 16 feet long. It's going to carry 200 PLF distributed load. And then at dead center, it's going to have a 1,200 pound concentrated load. The beam's section is 3 inch by 14 inch. So let's do the shear diagram. Well, let's find the reactions first. The reactions on this, you're just going to do 200 times 16. So it's 3,200 pounds for that. Add the 1,200 pounds for the concentrated load. You have a total load of 4,400 pounds. Since it's symmetrical, you divide it by 2. Each reaction is 2,200 pounds. So our shear diagram, we're going to have 2,200 pounds straight up. Slopes down at 200 pounds per foot over 8 feet. 200 times 8 is 1,600. So I'll take it down to 600 pounds of shear right here. 1,200 pound concentrated load takes it straight down 1,200 pounds. Puts us at negative 600 pounds. And then we slope down again at 200 pounds per foot for 8 feet. Takes us to a negative 2,200 pounds. Moment diagram. Well, we said a slanted line on the shear diagram turns into a curved line on the moment diagram. This is going to be curved like this. And then it's just the opposite over here, so it's going to curve down on this side. The height of this is just going to be the area of this trapezoid. So this being 8 feet, we've got 2,200 and 600 makes 2,800. Divided by 2 is 1,400 times 8 feet gives us 11,200 foot-pounds. So to analyze this beam, we need to first deal with flexure strain. Our flexure strain is going to be found using First, we need to know M, which is our maximum moment, which is 11,200 foot-pounds. But in the formula, we need that to be in inch-pounds. We're going to multiply by 12. So 134,400 inch-pounds will be our M. And we need to know a section modulus. Section modulus, remember, is just the moment of inertia divided by the width at whatever point we're looking at. Well, this beam is always 3 inches wide, so C is going to be 3. I, the moment of inertia, we're going about this neutral surface there. Neutral surface is always horizontal. And let's see, it's 3 times 14 to the third over 12. Gives us 686. That's inches to the fourth is what the units are on that. So S, or section modulus, is I of 686 inches to the fourth, divided by C, which is 3 inches wide. So 686 divided by 3, 228.67 inches to the third. So there's our section modulus. There's M. So our bending stress, 134,400 over 228.67. $587.75. This is going to be pounds per square inch. Now, this is a wooden beam. We didn't give our specifications yet on the wood, but if we look in our tables in our book, generally the table on page 278 is the most reliable for this. For wood, if you're looking at FB for bending stress, well, the lowest value given there is 1,000 pounds. That's if you have a hemlock fir. We usually assume either southern pine or a Douglas fir. So it looks like we're looking at about a 1,300 psi or 1,550 psi. We figure just a Douglas fir, 1,300 psi, we're still well, in an acceptable range for bending. So this beam is safe for bending. Well, let's look now at shear stress. Shear, if you recall, is a little bit more tricky. FV, the shear, is equal to V, which is the value from the shear diagram, times Q. Q is called that first moment. Q is the area times Y bar. What's the distance between the beam cross sections, neutral surface, and the centroid of the area above or below where we're looking at. And then over I, the moment of inertia, and B is the width of the beam at the desired plane. Now we want the maximum shear. The maximum shear is going to be at the neutral surface. So neutral surface goes through the centroid. Since this is a rectangle, the centroid is in the center, halfway up, 7 inches from the bottom. So to analyze this, we look at the maximum value for the shear. If you look at that, it's at the reactions at 2,200 pounds. So V equals 2,200 pounds. I, our moment of inertia, we already calculated, was 686. B, always 3 inches wide. Q, we need to find. Q, remember we said, is the area above or below the axis or the surface we're looking at. So we just take this up here, and that is the distance of its centroid times its area. So that's going to be 3 by 7. So the area is 21 inches squared. Its centroid's right here. If this is 7, that would be 3.5 inches above the neutral surface. So 3.5 times 21 gives us 73.5 inches to the third. So that is Q. So we set this up. Our sounds like a lively conversation next door there, doesn't it? We have 2,200 pounds times, let's see, Q is 73.5 inches to the third, over I, 686 inches to the fourth, times B, which is 3 inches. As you can see here, the inches are going to cancel out. We're going to get pounds per square inch. PSI, which is what we want. So we're going to 2,200 times 73.5 divided by 686 and divided by 3. 78.57. That is pounds per square inch. Shear is generally pretty low. Unless you have a really long beam or an extremely heavy loading condition, shear is going to be a relatively small number like that. It generally does come out to be pretty acceptable. Most beams do not fail in shear. Just to compare the acceptable value for shear, if we're still considering a Douglas fir beam, up to 85 psi. So that one's actually getting kind of close. What we're looking at, the reason that the shear stress is so low, the 85 psi, it's not longitudinal shear that's going to be the problem. It's the transverse shear, or not it's not the transverse shear, I should say. It's the longitudinal shear. Transverse shear, its tendency to shear off in this direction. The grain structure is strong there. It's not going to shear off in that direction. Where the issues come is the fact that you got the grains, you got these fibers running this way. I don't know if you ever taken a short piece of 2x4 and just stood it on end and whacked it with a hammer or whatever. You can actually get it to split along its grains. And that's what happens in a beam. The grains run that way. It can actually split along those grains because of this shear. That's the longitudinal shear. So that's why we're limited to only 85 psi is our shear stress limit. That's the FV critical. So we are acceptable for shear here. Well, then our next stage is to see if we are acceptable in bending. To check that, we have to look at some formulas in our book. Our bending formulas are found. Where are you? On page, I think it was somewhere around 410, wasn't it? There it is, 406, 407. We have our beam deflection formulas. This is what we started on Tuesday. Yeah. This is what I screwed up on Tuesday. So when we're dealing with this, we have 16 feet of a 200 PLF with a 1,200 pound right in the center. So that means we have a continuous load and we have a single centered point load. So we have to combine the two formulas. So for the continuous load, the amount of deflection is going to be 5 times omega, which is 200, times the length, which is 16, times the length in inches, 16 times 12 to the third power. The book says 5 omega, then L to the fourth, but one of those L's has to stay in feet to give us the total weight. The other 3 L's do have to be converted into inches before they're cubed. That's going to be over 384. E is our elastic modulus for wood. Let's go back to our table here. Assuming we're still under Douglas fir, beams and post, 1,600,000 is E. And I, which was 686. So remember that formula was, oh, it's in the book in 4 or 6, you can see it. So then we're going to have to do 5 times 200 times 16 times, so since this one's cubed, we got to do it in parentheses, 16 times 12, close parentheses to the third power, divided by 384, divided by 1,600,000, and divided by 686. 0.269 inches. Then we also have to consider then the deflection due to the single concentrated load. If there is a single concentrated load, the deflection is the point load, the 1,200 pounds, times the length to the third power, so that's 16 feet times 12 to the third power, over 48 times the elastic modulus times the moment of inertia. So 1,200 times 16 times 12 to the power of 3 divided by 48 divided by 1,600,000 divided by 686. 0.161 inches. Now we're going to add those two, 0.269 and 0.161. We're going to get 0.430. Now if we assume that this is a floor, we look in our table for floors, back on page 403, for floor beams in ordinary use, and we analyze live loads at L over 360 and dead loads at L over 240. What we did here was the live loads. We're going to have to do an L over 360 to get the allowable deflection. So L is the length, that's 16 times 12. We're going to divide that by 360. So 16 times 12 divided by 360 gives us an allowable deflection of 0.533 inches. So we were under the limit for bending stress. We had 587 and we were allowed up to 1,300. We were under the limit for shear stress. We had 78.57. We were allowed up to 85 psi. And we are good for deflection. We deflected 0.430 inches and we're allowed 0.533 inches. So this beam is adequate. Any questions? How many of you think you can handle that on your own? Like on a test next week? Maybe? I would probably not be too much more difficult on you. I would maybe do something like throw in an I-beam. Let's say we're going to do a 20-foot span. Say this is a 400 PLF. And we have 2 point loads, 1,000 pounds each. Let me make this span a little different so it's easier. Let's make that an 18-foot span. That way we can divide it into 3 equal pieces. 6 feet, 6 feet, 6 feet. Okay? And let's say this is an I-beam. Let me find my I-beam chart so I get a decent one. Let's do a W1860. It's a W18 by 60. It is steel, A36. So A36 steel, we go back to the chart. Has elastic modulus of 29 million. Moment of inertia. Go back to our table. 1836 is what? Or 1860, I should say. W1860 has a moment of inertia. 984. That's back in the appendix. The W1860 I found on page 571. From the W18, then you go down to the 60, then you follow it over. IXX is, where was it? 984. So I is 984. Okay, well, so we go back through the cycle again. Bending. Well, let's do the diagrams again. We're going to do 400 times 18 to get the total load for the distributed load, plus 2,000 for the two concentrated loads, divided by 2 gives us 4,600 for each reaction. So 4,600 pounds. What that means, up to 4,600, 400 pounds per linear foot for 6 feet is 2,400. Takes us down to 2,200 here. Down 1,000 pounds, takes us down to 1,200. Slanting through here, takes us to negative 1,200. Down 1,000 pounds, takes us to negative 2,200. Slanting, negative 4,600. Moment diagram. It's going to curve up again, curve down, sloppy curves, but we just have to find the areas to get the numbers. This value is the area of that trapezoid. So 46 and 22 makes 6,800, 3,400 times 1,200, or times 6 feet, I should say, is 20,400 foot-pounds. And to that, we're going to add the area of this triangle, which is 1,200 by 3. That's another 1,800. So 1,200 times 3 divided by 2. So that's going to make this point up here 2,200 or 22,200 foot-pounds. So let's try to do our bending analysis here. Well, we need to get our, let's go back to our table here. Page 571 again, W1860. Does it give us a section modulus? Yes, it does. SX is 108 is our section modulus. So we're going to use that in here to find our bending stress. It's going to be our maximum moment, 22,200 times 12 to turn that into inch pounds, divided by the section modulus of 108. So 22,200 times 12 divided by 108. So 2466, 2467 we're going to call it, PSI. If you check our table, again, back to that same table on page 578. A36 steel, bending stress 22,000 pounds. We have gone over our bending stress, so this one fails on bending. Let's complete our analysis though. Shear stress. Now steel has a really high shear stress. 14,500 is its allowable shear. Let's see what the shear stress comes out. Now since this is an I-beam, our average shear stress comes out to be V, which is 4,600 pounds, is our largest shear off the shear diagram, divided by the web thickness. Let me get back to the appendix again. 571. A W860 has a web thickness TW of 0.415 and a depth D of 18.24. So what goes in here is simply 0.415 times 18.24. So we've got 4,600 divided by 0.415 divided by 18.24. Oops. That should be 607 or 608 is what that should come out to be. PSI is the actual shear stress. I had a decimal. I left the zero out. That's why it came out to 60.8 instead of 608. So in shear, it's okay because we're allowed 14,000. We got 608. So it would have been okay for shear. Obviously, this beam is going to fail because we failed bending. But shear would have been okay. What that means is we need to find something with a slightly higher section modulus than 108, by the way. So you could go through the appendix there and look at the tables for the I-beams and find something that has, probably you have to get up to like around 120 or 130 to get this below 2,200, or the allowable 2,200 pounds. Let's look at the deflection. Well, you guys can do the deflection formulas, can't you? You guys are comfortable with those? Or you just want to see one example? One more example. One more? Okay. So for deflection, we have a 400-pound PLF, 18 foot, and we have, oops, we have 2,000 pounds over 18 feet, 6 feet apart. So for the PLF, it is going to be 5 times 400 times 18 times 18 times 12 to the third, or 384 times our elastic modulus was 29 million. And our moment of inertia was 984. Let's calculate that out. 5 times 400 times 18 times 18 times 12 to the power of 3 divided by 384 divided by 29 million and divided by 984. 0.033 inches. Not much deflection from the distributed load. Let's look now for the equally spaced 2-point loads. That's going down to the third formula. That's going to be 23 times P, which is 1,000, times L, which is 18 times 12 to the third power, over 28, oops, or 648 times E times I. So let's take a peek. 23 times 1,000 times 18 times 12, third power, divided by 648, divided by 29 million, divided by 948. 0.013. So 0.046 inches is the actual bending. Allowable bending would have been 18 feet times 12 over, let's assume it's a floor, we'll go L over 360. We would have been allowed 0.6 inches. We only had 0.046. We're good. So it was just the bending that killed us here. Let's go back and figure out what this would have to be now that we know that it fails in bending and it holds in shear and deflection. We just got to figure out what this needs to be. So we've got the 22,200 times 12. That is the bending moment. We're only allowed, what was it, 22? I better look it up. Going back here for steel, 22,000 is what we're allowed for that bending stress. We need to find what this section modulus would be here. So that's actually going to be 22,200 times 12 divided by 22,000. 12. Why is that not look right? Did I calculate something wrong up here when I did it? Let me try this. This is back to the bending stress formula. Actually, you know what? We didn't fail for bending, did we? It's not 2,200 for bending, it's 22,000. So we're good for bending. A36 steel is 22,000, it's not 2,200. So we're good. We can be up to 22,000. So that was okay. What we would have done if it wasn't okay is you would, like I was doing here, you go back to this formula. Where did I put it now? And you figure out what you do is you put your actual moment from the diagram, of course, times 12 to make it inch pounds, divided by what your allowable bending stress was, and that'll tell you what your section modulus has to be. So you can look in the chart and find a beam with a little bit bigger section modulus or whatever to make that work. Okay, this looks like a good spot to take a break.